Last topic is center of mass as it relates to translational motion. Both of these concepts should be pretty clear by now. And one of the big factors here is knowing that the motion of the center of the mass is always going to be the same as treating that entire object like it is one point that is the center of mass. And so that means that the net force on the whole object will always cause the exact same motion that the center of mass goes through. And that's why you can have one arm flailing forward and the other arm flailing backward, and still the net force is the same as the net force that the center of mass experiences. So let's take a look at three particles on an x-axis with mass A, mass B, and mass C. And they're at positions xa, xb, and xc. So this is a system. And we could determine the overall net forces and net momentum for them using just the center of masses. So remember, momentum is conserved. So the momentum of the center of mass for the object will be equal to the momentum of the sum of each of those objects. So we could just consider those values. But we can also find the center of mass. And what we do there is we can use the velocity of the object to determine the net displacement of the object. So what we're doing here is we're looking at a simple case of one-dimensional motion in the x direction. And even though there's three different objects, we're going to treat them all as just their center of masses. So we could find the center of mass, and that center of mass would be located somewhere in between those objects, where the big M is equal to the sum of all of those masses. If those particles are in motion along the x-axis, then they would have velocities, and each of their velocities would be VA, VB, and VC. Those velocities, given by the equation of change in position over time, would be given. Therefore, you could find their displacement by this equation. The displacement will be equal to the velocity of object A times the time that it was displaced. And here, the prime is represented by the final position. That's simple kinematics. Now, that means that the center of mass initially could be given by this equation. The center of mass after could be given by this equation. So the change in the center of mass location could be given by combining those two equations in. And now we can substitute, instead of the change in position here, we can substitute in the center of mass's velocity times time. So if we do that, mass times velocity of the center of the motion times time, you get this VCMT gets replaced with VAT, VBT, and VCT. And now you have time in every single variable, so out goes each of those times. And you get, hey, look at this, what is this? This is MV, that's momentum. MV, that's momentum. MV, that's momentum. MV, that's momentum. And so we actually get that the center of mass and the momentum of the center of mass for an entire system is going to be equal to the sum of the center of mass's momentums for each individual object. So that's for a system where there are no external forces. If there are external forces, then we wouldn't be using conservation of momentum. We could, in fact, just use force times acceleration. If you're using net forces, if you're using Newton's second law, then you get that we know that our acceleration equation is change in velocity over time. So here we have that change in velocity for object A will be equal to acceleration times time. And likewise, we repeat it for object B and object C. So here, if we're doing the net forces, then you have the net forces for the object's center of mass, mass times acceleration for the center of mass, should be equal to mass times acceleration for A, mass times acceleration for B, and mass times acceleration for C. And since mass times acceleration is equal to force, that means that the overall force or net force experienced by that center of mass is going to be equal to the sum of the forces experienced by all of them. So that means that the net force, which is exactly what that equation is, will give us the net force experienced by the center of mass. And that's a pretty dang convenient situation to be in. So let's take a look at a conceptual example of this very phenomena. You've got a two-stage rocket, and that's what this is. It's a rocket where you have two sets of motion. It's shot into the air, and at the moment the rocket reaches into its highest point at a horizontal distance d from its starting point, so that's this value d here. A prearranged explosion separates it into two parts of equal mass. Part 1 is stopped mid-air by the explosion, so that means that that part has no x velocity and it falls straight to the ground. So the momentum of that object has been reduced to 0. Since conservation of momentum is at play in an explosion, that means that part 2 should increase its momentum, and as a result of increasing its momentum, it's going to follow its path, which is a projectile path, over here. And if we were going to try and figure out where it ended, we could figure out using the path of its center of mass, because remember, the path of its center of mass should be conserved. It should be the original pathway. So that means that after the rocket is fired, the path of the center of the mass continues to follow the same trajectory that an object would travel if there were no forces acting on it. So that means that this pathway would be calculated with simple kinematics. Alright, and that would give us this pathway. We could pretend the whole object stayed together, but since we know it broke apart and we know the pathway of this part, we could then figure out what pathway would this object give us that would give us the center of mass adding up to the center. So that means that the center of mass lands at point 2d, which is, if it's d up, it's going to be d down, according to the symmetry of kinematics. Since the mass of 2 and 3 are equal, the center of mass must be midway between them at any point in time. So that means that since m1 and m2 are equal to each other, given by our center of mass equation, the center of mass should be exactly halfway between them. So that means that part 2 actually ends up 3d away from the starting point, since we know that the center of mass has to be d between them. So that means that a two-stage rocket can actually go 1/3 farther than a one-stage rocket. And the larger this mass is compared to this mass, the closer the center of mass is going to be to it, so the further it falls, or the closer it falls to its original pathway. If this mass is larger, then the center of mass is going to be closer to this mass, which means that this one could travel potentially even further.